In this tutorial for Midas Civil, I will show you how to model this cable stayed bridge and how to perform all kind of analysis on it. Cable stayed bridge are structural systems which are composed of cables, main girders, and towers. This bridge has a beautiful appearance and easily fits in the surrounding environment. And cable-stayed bridges are structures that require a high degree of technology for both design and construction, and hence demand sophisticated structural analysis and design techniques when compared with other types of conventional bridges. In addition to static analysis for dead and live loads, a dynamic analysis must also be performed to determine eigenvalues. Also, moving load, earthquake load, and wind load analysis are essentially required for designing a cable-stayed bridge. To determine the cable pre-stress force that are introduced at the time of cable installation, the initial equilibrium state of the dead load and the final stage must be determined first. Then construction stage analysis according to the construction sequence is performed. So in this tutorial I will explain you how to model this cable-stayed bridge, how to calculate the initial cable pre-stress forces, and how to perform the construction stages analysis and review the output data. So I will do this tutorial in two main parts. One part this week about the modeling of the bridge and the calculation of the pre-stress in the cables, and next week I will talk about the construction stage analysis of this bridge. Let's look first at the bridge dimensions. So this is the bridge model that I will use in this tutorial, and actually it is a simplified model because it is just for the purpose to explain how to model a cable-stayed bridge. Then the bridge type is a 3-span continuous cable-stayed bridge, self-anchored. The bridge length is 420 meters, divided in 3 main spans. The bridge width is composed of 2 lanes, and the total width is 15.6 meters. Now let's close this model and open a new project, and we will begin the modeling from the beginning. So the first thing we'll have to define are the material properties. So to do that, go in the material property tab and add a new material. So if you watch this table, you saw that we have to add 5 different materials: one for the cable, the girder, the pillon, the C-beam girder, and the C-beam pillon. And these are the coefficients I will use. So we'll first create the cable material. Enter the name of the material, cable. We'll choose user-defined material, and we will define manually all the coefficients for this material. So here the module of elasticity, which is 1.9613 power 8, the Poisson's ratio 0.3, and the weight density. These are the 3 main coefficients we need to fill in the material, and click on apply to add it to your material properties. Now let's do the same for all the 4 remaining materials. The girder 1.995. Okay, apply. The pillon 2.787, 0.2, and 23.56. Apply. the C-beam girder, (1.96), so it's the same property than the girder. And the C-beam pillar, (2.78 power 8), 0.2 and 23.56, and click on add. Now we'll add some sections which are corresponding to these materials. So click on add, click on the value tab, and we'll enter the section properties. So in this section property table, you have all the properties to fill for the sections. So for the first one, call it cable. Don't forget to check these two options, bolt up section and consider the shear deformation. For the section, we'll choose solid rectangle, and the area will be 0.0052. Now click on OK to add this element. Now we'll do the same for all the different elements. So I used the wrong name, so it is the C-beam pillar, so we'll just use the modify option to call it girder. Okay, and I just have to do it again for the last one.